Good. So welcome everybody to our third lecture of the ARIVE lecture series. Again, 3 p.m. New Zealand time. So thanks for coming. My name is Tobias Langlotz. I'm here from the University of Otago, where I co-lead together with Holger the HCI lab. I can't see you, but I see that a couple of people, or quite a few people actually in there. If you have any technical problems, please use the chat, and I hope someone else will make me aware of the problems we try to sort out. Otherwise, I will just make a start with today's topic. So last week, we have actually heard the introduction from Holger, and we got a quick background on general terms and definitions, but also general concepts in augmented reality from Alex. And today we slightly transition, or we start to transition and actually into the research part. And I want to close that gap with actually something that is a bit research, but it's also still covering a bit fundamentals. And this is, I want to talk about optical see-through head-mounted display. So I placed that prop here. So you all know devices like the Microsoft HoloLens. I hope all or many of you have tried that. And I want to talk about achieving with those optical see-through head-mounted displays something that we call towards indistinguishable augmented reality in optical see-through head-mounted displays. So the idea is, and that's what actually the title shows, that we want to achieve something, fidelity of overlays using these devices that is almost indistinguishable from reality. And that's what's today's talk about. Okay, so let's start a bit with the motivation for this talk. Why do I pick that? Why I'm interested in that? So generally what we know is, and what Alex covered last time is, we know that these optical see-through head-mounted displays, they're out there for quite a long time. In fact, one of the first AR systems by Ian Sutherland was already an optical see-through head-mounted display. So you see in the top row, so sometimes also called the ultimate display or the sword of Damocles. But since then, a lot of time has passed by. And now we have devices like the HoloLens, but also the Magic Leap that created quite some media, created quite a media attention, but also gave us new tools as researchers, because suddenly it gave us quite powerful optical see-through head-mounted displays. So, and I think also the professional people, so the working in the industries, they have now realized more the potential of these devices, and for the first time, they're also able to buy these devices. And they're not just the Magic Leap, but also the and the HoloLens, but also other ones. So here are some devices that we used in the lab here, but also in the lab from Yuta Ito, who worked with me on that topic. So, and just to be sure and to recover from, or to make sure also from last time, today I want to talk about optical see-through head-mounted displays. So everything that is somehow surrounded by the green, those are optical see-through head-mounted displays. I will not cover today and talk about video see-through head-mounted displays. If you're still unsure about the differences, particularly I'm looking to the students here, then please revisit the lecture by Alex. Okay, so again, why are we interested in? Because we are interested into creating this visually indistinguishable augmented reality experience, and we were working on that for quite some time. So we had quite some contributions to achieve that. But we were also recently looking into all the other works have been done. You know what a survey or review paper is. So we started to look into that. And over the last, I actually have to say, it's over the last 4 years, we reviewed and discussed 170 papers in the field that cover hardware as well as software to achieve that goal of visually indistinguishable overlays in these head-mounted displays. So we focused in that work on academic papers, so we didn't look so much on patents or non-disclosed implementation details, because it's always a bit unclear what has been done or not. And we wanted to look into unique issues in optical see-through head-mounted displays. So there are a lot of problems, for example, in photorealistic augmented reality, that is not unique to this kind of see-through head-mounted displays, but they're generally relevant in augmented reality. We didn't look into those. And again, the goal is to achieve visually indistinguishable AR overlays. And we looked into that, and we identified 3 main issues. So those are spatial realism, temporal realism, or temporal issues, and issues with respect to visual realism. And in today's talk, in today's lecture, I want to talk about all of them. introduce you what are the actual issues, why is it relevant, why is it important to solve these problems. And even though I will run out of time at the end, I already know it, I want to briefly talk about some of the solutions that exist. I have to say, before we dive more into that, or I indicated that there's a paper that we worked on. Actually, this paper is submitted. I was hoping initially that we will have the reviews back by now, but that's not the case. But I still feel confident about talking about that, mainly because it's a single blind review process. So basically, if the reviewer is even out there, you know anyways that the paper is from us because we said it on the paper. So I think it's okay. What we will not talk about, but talk in today's lecture, but talk about in the paper is fundamentals on the human visual system. So how is our eye built, so the physiology, but also the perception. I will scratch a bit on that, but we will not go into any detail. I will also not talk today in any long detail about the basic optical designs of optical see-through head-mounted displays. So there are many, I feel confident it's certainly over 50, probably 100 different design approaches and optical designs of optical see-through head-mounted displays. And if you look into optical journals, it's full of them. And because of that, because it's such a big topic, I kind of excluded that from today and will only occasionally bring one in, okay? But if you're interested in, once our paper is hopefully published, you will still find a lot of resources there. So let's start and look into the first problem. And the first problem is about spatial realism. And you will see today a lot of hands with apples because I use them always a bit to on the high level to illustrate the problem. So what you want, that's usually how I explain it to other people. What we want is what you see hopefully on the left-hand side. And this is, you want to have your real hand and you want to put an optical see-through head-mounted display that is rendering an overlay on an apple, and you should have the feeling, visually at least, that the apple is in your hand. So something like this on the left-hand side. But actually, when it comes to spatial realism, you might get a result realistically that looks more like on the right-hand side. So the apple is somehow looking a bit different, it's somehow distorted, and it's certainly not in your hand. So why is that? So first is because we need to do something, it's a spatial calibration, and this is because our eyes and heads are different. Here, Holger borrowed me his quite beautiful head and his beautiful eyes, and you see basically his eyes, they are in a certain position with respect to the display. So what might happen is, first of all, he might move it around, and every time he's wearing the HoloLens, he's wearing it slightly different. Moreover, my eyes have a slightly different distance, and they're differently positioned with respect to the display. And most of the displays, like the HoloLens, they don't take this into account. What they take into account is interpupillary distance, so the distance from our eyes. But again, if I wear it slightly off and move it, for example, because I scratch in my nose, that is not corrected. And that leads to a missed registration or to errors in registration. So just to have this video, so these videos that hopefully run that show this, so they have more than just a misregistration, but they also have latency. But what you see, it's actually, you want this overlay to be on top of that marker, but it never really aligns. It's just roughly somehow there, yeah? What we want, that even in the case here in that video of latencies, that we want, like on the right-hand side, that it snaps at least back as soon as we move. So this is, again, there are a couple of other problems here because it's also latency, but here now you see once we stop moving, it snaps back. So it's very precisely aligned. And this is not something that we can normally achieve with a Microsoft HoloLens because it has nothing to do with a very precise tracking, but it requires that we do a display calibration. Sometimes it's also called eye display calibration. And there are lots of different algorithms for that. Probably the best known one, which is almost 20 years old, is called SPAM, so single point active alignment method. So the idea is that you have a camera either integrated in the HMD or externally, and that you click or that you look with your camera in well-known points, usually markers, that's what you see on the right-hand side, and that you really align that with a crosshair in your display so that the external camera seeing this marker can position the pose, but you also align it with points in your display. And you do this for multiple points, and then under the assumption of a simple projective geometry, you can use very similar algorithms to standard camera calibration, okay? So I just show you that video, how this looks like. I should notice, I forgot to put the reference here, that's from Ed Swan and Kenneth Moser's work. So this is how you see it. So you just click, you have that crosshair. Now you go to the next crosshair and you always align it with that marker, and you do that for different positions in your display. And after you did it for a couple of points, you get a quite decent calibration of your eye with respect to display and to the real world. The problem is, again, it requires manual input, but also, again, if you scratch your nose or if you move, then you might invalidate this calibration, okay? So what we want is actually ideally something that can be done automatically, or that is done continuously. So there are also other approaches, so more recent approaches. They are more into this direction of interaction-free display calibration, so they don't require that you click anything or line something. There still is some assume simple projective geometry, but what they need to do, they try to take an integrated eye tracking camera, and this is what you see in the image, is basically the red camera with a T that is looking at your eye. And then you can either tracking your eye, or there's also another approach by Alexander Plopsky, who's also here in the room, who's looking into the reflection of your eye. You see it probably in the lower image, the reflection of that specific marker, and they're analyzing this. But the general idea is that they compute, those approaches compute an exact model of your eye, but they also need to know or have an approximation of the display and the display surface. Okay, so there are a couple of requirements that need to be taken beforehand. If you have all this, and if you can track your eye, then you can compute a quite good alignment continuously with no user input, and you can continuously update. So even if you move your head-mounted display, as long as we can see your eyes, we can update this calibration and make sure that, that you see quite a good overview. Okay, so and this is basically the state of art of research. So there are approaches. So it's still not fully solved because also eye tracking is challenging. And just recently we see this integrated in optical see-through head-mounted display. But it's required for good spatial alignment. Another big problem when we talk about spatial realism is distortion in head-mounted display. And I will not have too much time on it, but I just want to show you the effect. Often when we talk about head-mounted display, like the HoloLens or optical see-through head-mounted displays, we talk about that there is a focus plane. So we always give the illusion that there's a plane, and this is the plane or the image plane that we see. But there are a couple of problems with that. First of all, this is what you see on the left-hand side. On this image planes, points are not sharp. So this is a work by Yuta Ito's group. So what we see there is actually he made with a camera, he switched individual white pixels on that image plane, and he made a photo of them with a camera. But what we see, these white pixels, they don't look like white pixels. They're actually very blurry, they are more lines, and we see actually chromatic aberrations. So basically we see that this white pixel goes into the base colors. You might see that slightly red on the left-hand side, the green part and the blue part. And the problem is also this distortion and blur is not uniform over the head-mounted display. That's what you see in the center. So these are multiple white pixels distributed over the head-mounted display. And you see that they distort in different ways. And this is because of the imprecision of the optics. And what this also leads to is what we see on the right-hand side. So this is some researchers, a couple of people did that. This is a picture from a paper from Clem et al. What they try to do is they try to reconstruct actually what we normally call the image plane. But the image plane has nothing in common really with a plane, because actually if you would do a reconstruction, and this is what those guys did, they found out that actually the focus or image plane, focus plane, is actually more like a spherical surface. And that's what you see on the right-hand side. And because of that spherical surface, points are again blurred differently and behave very uniformly. And all those effects are highly view dependent, which is very hard to correct, but it's still an active research area to improve on that. And one way is to improve it with better optics, can be very expensive. The other way is you do software algorithms, and this is what the research is going towards. Okay, so I still wanted to show it to you there, because otherwise we would need half an hour at least to dive into possible solutions for that, so that you at least are aware of the problems that are there. The other big problem is temporal realism. So I made this photo, and I'm not. I made this small video, and I'm not sure of a zoom if it animates as smoothly as here, but I hope it makes it quite clear. Certain elements, like for example the apple, will not perceived be as realistic if they are subject to large effects like latency or flicker, which is not shown here. So what's the problem with latency? So latency is relatively well known, and almost with all computing systems, we are subject to latency. In the context of VR, also latency is relatively well explored, and we know it's the main cause for simulator sickness. There are also studies in VR that looked into how much latency can we actually tolerate. So there's a paper that shows that actually it's perceivable in VR down to 5 milliseconds. And this is often taken as the standards in our field, that they say we should aim for latency below or maximum 5 milliseconds. That is roughly in line with studies from HCIs. So they also investigated perceivable latency. They said it's below 17 milliseconds, but they also said that the user performance can be affected by latency as low as 2.5 milliseconds. So they did studies, that's from these references, where they showed you, it's not with an optical C4 head-mounted displays, where they basically you drag objects that are projected with different levels of latencies. Yeah, so now you see it with 1 millisecond, and I think this video is even slightly slowed down as far as I remember. Yeah, so this is some of the apparatus that they have used to investigate it. So, but in generally, I think 5 milliseconds is something we should aim for. At the same time, there is flicker, which is another temporal effect. So those of you who are old enough that still know all the old CRT screens, and they still knew that they were quite susceptible to flicker, and that can be really annoying. Nowadays, displays are better, and normally we say that we should aim for 90 Hertz, even though this critical flicker frequency, so what we perceive as flicker, is not uniformly, okay? Because basically in our periphery of the eye, we are more susceptible to that, while in the center we are less susceptible. However, even there are some papers that show if you have just the right, or in that case the wrong pattern, we can perceive it at still 500 Hertz. So it sets quite a high bar. And there are a few works that looked into flicker and into latencies, and that's needed because if we look at the HoloLens, and this is, I'm talking here about the HoloLens first generation, so there usually we have an update rate of 60 Hertz and roughly 15 milliseconds. This is just the display latency, okay? So we are far away from this 5 milliseconds. But there are some research works that look into it, and in particular here, the group from Henry Fuchs published a series of really cool papers that really looked into how to reduce latency. And they really did a great effort and used a lot of machinery, for example, a mechanical low latency tracker to investigate it. And probably most well known is the paper from Motion to Photons in 80 microseconds, so where they had a reduced overall latency. So because they used a mechanical tracker, but they also had a low latency display. So it was a custom display, and you see when I show the video in a second, it has not much in common with a really head-mounted display. It's more a projector that shows possible future design for head-mounted displays. So what they showed here, so they moved this head-mounted display prototype. So you see that's the standard approach, and you see that it's lagging behind. Yeah, so basically there is no precise overlay. And this is their approach, and you still see there's a bit of latency at the end, but basically it's well better, okay? And the key to achieving this here is that they used actually something, so this is actually slowed down, that shows the effect probably a bit better. They used actually digital micromirror devices, so something that you see in DLP projector, which has millions of small mirrors that can be controlled extremely quick. And this mirror basically reflect the light and are used to create that image. But the idea is that you don't send out the mirrors or the image and render it fully, but as soon as you get new tracking information, you adjust and update the position of the mirrors, so how they send light or not. So basically, as soon as you get new tracking, you start to send out new light information, create a new image, okay? And there are a couple of more works, but it's very important, and it's often, how should I say, I would almost say, and it's not appreciated even though these papers have been very well received. The last and biggest topic is probably visual realism. And the visual realism, again, showed it here just in Photoshop art creates lots of effects. So again, if we show the apple, first of all, we have a reduced field of view. Usually with current head-mounted displays, we have often low resolutions. The colors are off, but also that apple usually somehow sees transparent. And there are way, way more effects that I could show here, but I want to quickly talk about them. So one of the biggest problem for me personally in visual realism is color. And that is often not mentioned. So what is the issue with color? For that, I want to look in a very simple setup of an optical see-through head-mounted display. So this is an Epson BT100, and imagine we see it here from the top. And I just want to use it to explain some of the basics, what's going on in a typical optical see-through head-mounted display, even if you use a different design, yeah, because it's just very easy to understand. So what happens is first of all, they're transparent, so you see roughly, again, this is seen from the top where the user eye is, and normally the environmental light would go through this half-transparent display. But to make it a display, we have a display unit, and this is what on the left-hand side, so we basically have a backlight, usually it depends on the display technology and the display panel, and we have a couple of projection lenses that basically project that image into something that's normally called a light guide or a wave guide. And what this one is doing is actually transporting the projected image to your eye. There's something like an exit pupil, and this allows the projected light, to exit basically that light or wave guide and go into your eye. And again, they're very different approaches, but they often have all these components in common, even though they could look quite differently. But all the problems that I will now show, they are common to all of those. So what's the problem when we talk about color, when we look into a general see-through display like this one? So the first thing is the display, and it's common to all kinds of displays. So the first what's wrong with displays and colors? Well, displays use a wide range of color spaces. So you probably have seen this image on the right-hand side before. So that's basically the color space that we humans can perceive. And often you see these weird triangles in there. And these are, as you see here, and these are usually the range of different RGB color spaces. And what you can see there is most of these triangles, they don't cover the color range that is depicted there, basically, that humans can perceive. So basically, most of the displays cannot create as many colors as we can see. So there's always a reduction in color space. But the other problem is that it varies between the devices. So these are normal color spaces, but most displays, and in particular displays and used in optical see-through displays, their color space is even smaller. So there is actually, we cannot show all the colors that we can perceive, and it varies between the displays. And that leads to degradation in color. That's the first problem. Again, there's a paper from Yuta Ito's group that showed and tried to correct that. So what they did, and this is what you see here in the picture, so they made on the left-hand side, they made a photo. So you have that photo of a scene, donut, banana, and a very well-known book from the computer vision community. And he made this photo. Then he removed the objects and basically showed that photo in front of a black background and an optical see-through head-mounted display. And what you see is the middle one. And you see basically the visual quality is highly degraded. It's blurred, we come to that, but it's also the colors are quite off. And what he now did, he corrected for this, and what is you see, this is the result, is what you see on the right-hand side. And you can think about it as a complicated form of a display color correction. Okay, so he did a semi-parametric model. I will not go into the detail for that, but you can see that he's able to recover some of the colors. Okay, which is already leading to an improvement. What's the next problem? The next problem is the general optics and optical see-through head-mounted displays. And again, they might vary, but they all have some kind of optics in there. And optics, they can be almost perfect, but usually they are cheap, and because that they're not perfect. So I hope that among the audience here, there are a couple of photographers who are interested, because they will know about all these effects, like for example, aberrations. So there are different kinds of aberrations, imperfections in lenses, for example, spherical aberrations that you see here, or chromatic aberrations. So what they lead is that certain rays that should actually focus on one point, so this is the ideal view, that they don't focus on one point because of points where they enter the lens, but also because different frequencies, different colors, are refracted differently. So, and what this leads to is blur, and this links exactly back to the photo that we showed beforehand that shows, again, these are actually not three colorful rainbows, that should be 3 white points. Yeah, but we see actually that we see these rainbow effects, and this is because of chromatic aberrations, okay, because of imperfect or affordable optics used. The other effects, we see distortions. Also, this one we know from photography that are also in there, and they're also we also see them in optical see-through head-mounted displays. So, and I want to see just some of the results here and some of the effects that cause. So, on the upper left-hand side, you see an absent BT100, which is again one of the simpler and more affordable optical see-through head-mounted displays. It's photo made from a camera at the eye position, and we just show in image A a white image. So what you see, first of all, this image is not, the image plane is not really rectangular. We roughly talked about it, but it's also, we would expect a uniform white image, but it's far from that. Okay, it's quite non-uniform. You can correct this to some extent. So you can look what is the darkest pixel, and then you turn all darker so that they become uniform. And this is what you see on the right-hand side. So it's hopefully you can see it's a small improvement. But the problem is not just in cheaper head-mounted displays, but you also see this on the right-hand side. This is a photo what Alex Plopsky did here. So these are effects for individual colors taken from the same spot, but they show quite different degradations. So it's actually highly view dependent, but also frequency dependent. And what this result, and there I have to say, I stole the image from Karl Guttag's blog, but I linked to him to make that good. So because he had just a blog post entry, I think it was from the last week or 2 weeks ago, where he did the same with the recent HoloLenses. So he sent in a quite complex image, so the test pattern on the left-hand side, and you see in the HoloLens 2 and the result from the HoloLens 1, they look quite different. They are blurred, but you can also see that the colors are off. And these are really some of the best optical see-through head-mounted displays that you can get. And he's in very lengthy detail, even outlining and explaining why actually the visual quality, we could say, is actually worse in the most recent HoloLens. If you're interested in this, I would highly recommend his blog. It's really, really good. So again, so this was another effect for color. And the last thing which is affect colors is the effect of image blending. So what's the effect of image blending is, so far we always assumed, and you have seen this in the image from Karl Guttag, we had a black background, but this is usually not what the reality. Normally we move around here in the world and have a colored background. So we see the effects of the background coming through. So again, here 3 different images. Let's say A is the background, so color checkerboard, and want to show the image B, and this is then usually what we want to see. The reality, if we see it through a head-mounted display, is we see the background blending. Because it's a blending, we can't make it disappear because the display is half transparent. But often this is not what we want to see because it highly degrades the image quality, for example, of user interface elements and so on. So, and there are also a couple of approaches that compensate for that, and we were working on that a couple of years ago. And there we can learn from the community of projector camera systems, in particular from some of the work that was done by Oliver Bimbers and others, because they had the same problem with projectors. So if you project on a non-white or non-black, so basically non-simple surface, like here that curtain, you see the same effects. And they showed, so you see this here with the Finding Nemo movie, with a naive projection where you see basically the curtain shining through, and they proposed some methods that can, on per pixel base, correct that, and you see the result on the lower part. So back then I was involved in some of this work by Oliver, and I always thought we should apply this also to optical see-through head-mounted displays, and we did this, but before we are able to do this, we had to solve a couple of problems, and that is, we need to have an understanding of the scene. So how is the scene looking like? And actually we need to know that exactly from the perspective of the user. So so you can't use an off-axis camera like here, but what we did, we introduced another beam splitter so that the camera is almost seeing the image from the eye perspective. We applied some other software correction for the smallest changes. And then we applied a lot of math from it. And again, we benefited here from the prior work from Oliver Bimber's group. And then we are able to correct that. And these are some results here. So basically, again, on the lower row, on the bottom row, you see basically the background in the image that we show. On the left-hand side, the reference image is actually the image projected into in front of or shown in front of a black background. So you can't do better than this one. If an uncorrected, in front of now the colored background is the middle image. And if we correct it, this is what you see on the right-hand side. And I hopefully, even if you connect it via Zoom, you can see that there's quite a difference in the image quality, okay? Which is way closer to the reference image. Another approach that I still want to briefly touch about, there's the idea out there from a couple of groups, the Gordon Wedgstein groups from Stanford did this, and we also did this with Yuta Ito last year, where we looked into generally filtering the background. So we don't try to compensate it by rendering the color differently, but we just try to filter that out. So this is a prototype that we presented here, and actually it's not a display that adds light, it's actually a display that just filters light. But we could also reduce the image blending actually by a smart filtering. And that's actually everything I want to say at this point. So think about just not adding light, but filtering light on a per pixel base as demonstrated here. So again, all what you see here in the lower, this teapot or the too bright or the teapot on the right-hand side, this is just created by filtering light, not by adding light. There's no active light source in there, okay? In general, again, there are a lot of approaches there. And I will not go into too much detail and refer to the paper or that or the table here and the references at the end if you're more interested in different approaches for that. Normally, I also wanted to talk about high dynamic range because you might know that we humans, with the human visual system, is capable of perceiving quite a large dynamic range. But because of lack of time, I will not talk about it, but it's also captured in the previous table. But it certainly is a problem. Yeah, I briefly mentioned it here. So the biggest and probably most often discussed problem of optical see-through head-mounted display is the problem of accommodation capability. So what's the problem here and why is it relevant? So when we perceive the world, we focus on objects, and we focus on objects and basically create a sharp image in our eyes, doing two major effects. So the first is vergence, and the other is then basically focus accommodation. So vergence is basically then, for example, if I look at my finger, that basically my eyes, they move in their sockets so that they both center at that finger. And this is vergence. And the other effect is that there are muscles in my eyes, basically that change the shape of the lens, and they also make the lens to focus on my finger. And then the real world that works, I just checked here and I can still see the people sharp with the help of the contact lenses that I'm wearing. But there's a problem on optical see-through head-mounted displays because they work differently. Because the problem is here that we have, and this is what you see on the right-hand side, where we have a display screen that has a fixed distance. For example, for the absence, that is, I think, 5 meters or 7 meters. So it's quite far away, even though I might show objects that are, for example, again, in my hand, like this apple. Yeah. So basically what happens if I hold this virtual apple in my hand, that actually vergence is focusing on something 5 to 7 meters away, but focus I'm trying to do on the focus plane. Oh, sorry, focus is on something that is further away than the vergence, because the vergence is the whatever 1 meter in my hand. Okay, so and this is often called the vergence accommodation conflict. Can reduce usability and can also lead to quite severe headache. So again, just showing it here. So again, I have my hand. I want to show that apple, both should be in focus because they have both the same distance, but with that conflict. So either, and I hope you can see it, the apple is in focus, but the hand is out of focus, but also my hand is in focus and the apple out of focus, and I might get a headache. But it's always off and it's not certainly realistic. And this is often discussed. There are lots of different approaches, but we don't see any of them in commercial optical see-through head-mounted displays. So the first thing is what you can do is basically you just have the traditional approach, and this is basically you have a lens, you have a fixed screen, and you have this single focus surface, okay, which is basically where our image is presented. This is what we have in the HoloLens, and you see down there an image demonstrating that. The next thing is you can, and there is a commercial optical see-through head-mounted display, and I will never find it again. If you have an idea, please contact me, that allow to actually mechanically move the optical system. So basically the idea is you can't move it fixed enough, but if you want to have something in your hand, you basically adjust the focus plane so that it's roughly matching your working distance, or you can move it further away. So again, there is something out there. I will just not find that example again. More advanced approaches, what they do instead of moving it, they have usually varifocal lenses. So the idea is that you have a lens system that can change the characteristic extremely fast. So often they use even membranes for that. And what this allows us, because of the change in the optical system, is of the lens characteristic, to create a single depth surface, but that can be moved extremely quickly. So you can actually render at multiple depths. The problem is, again, we need a lens that is quickly enough to adjust it. And usually we also need eye tracking for that. Another approach is, if you don't have a lens that is quickly enough, you create actually, you use multiple screens and basically create multifocal surface. So basically the idea is that you have, for example, various LCD, sometimes transparent LCD layers, so that allows you to actually create different depth plane at the same time. So that is actually the Magic Leap is not really utilizing this, because it had actually two screens. It's not really, it's probably not enough to create many depth effects, but in theory, it's already an improvement. Okay, so you can that way create multiple of these focus planes. Other approaches is, some people have looked into light field rendering, so where you have micro lens arrays. So the example that you see down there are actually examples. They're not see-through, but there are see-through prototypes available as well that are a bit lesser known. So the idea is here that you create, again, a light field. And if you have a light field, and if you're familiar with light field, you get an impression of actually multiple focus planes as well. And the last and probably most sophisticated approach is actually that you really create an holographical optical see-through head-mounted displays. And there's a really cool work by Maimoni, for example, that shows you that's what you don't see there. And this is actually, it's really resemble what nature is. You create with a display what is called a complex wavefront. Okay, so that is really, you create a virtual image that you can really focus, like you can focus, you can hold your finger here, the rest is blurred, or you can focus on the background and then your finger is blurred. So it really creates an image like in the real world with all focus cues, which is relatively hard to achieve. It has a couple of problems, these approaches, but actually I think there's a general agreement that this is the direction and the way we should go. Okay, so I also personally think, despite some of the drawbacks, that this is the future. Again, there are lots of other approaches. I only presented here the main ideas, and I put them here into the classification. But I just want to show here there are many, many other approaches out there. But if you look into that and you just look roughly at the colors, you will also see green is usually good and red is usually not so good. They all have drawbacks, which is okay, but yet we have to find the really ideal one. Maybe we'll never find it. Maybe we have to accept some drawbacks, for example, a relatively large form factor, or maybe lower resolution, okay, for the next years. But we are yet to see some approaches like this in commercial prototypes. So, the last thing, and I already realized I will not completely finish today, but the last thing for today I want to talk about is occlusion capability. So again, to use that example of the hand and the apple, so I want to hold that apple in my hand, but I already said that actually we can only create, at the moment, standard approaches, transparent overlays. So even if we do color correction, there's still bits transparency involved, but what we actually want to create is really correct occlusion, so that the apple is occluding parts of my hand. This is what you see on the right-hand side. So again, this is an image from one of the publications from Yuta Ito, who gave me permission for that. And it's, you see the teapot, and the upper images with no occlusion handling. It's still, we can somehow see through, even though it should be a solid teapot, but we want correct occlusion handling so that this teapot is really occluding the real background. And there are a couple of approaches for that, and that contributes, of course, to the perceived realism. And a couple of different approaches for that. The simplest one is we just block selectively pixels on a per pixel base, basically light from the background. That's what you see there. And I always thought it's very simple. We just take an LCD, we put it in front of our eye and just block the eye, and then and just block the light. But I never, but I often forgot actually that's not as simple as that, because if you put a finger very close to your eye, you will see that it's actually blurred. So basically, if you put an LCD panel, a transparent one in front of your eye, and you try to block out light, that mask, and this is what you see on the upper left-hand side, is blurred. And this is often not what we want, because we want a sharp focus mask. But you can create this effect with different spatial light modulators, and this has been done, for example, LCD panels or DMD chips or LCOS liquid crystalline silicon chips. So that's a reflective LCD technique. But again, we cannot just simply put in the light. But what we need is actually, we need more optical lenses in there to really create a sharp occlusion mask. And that is what makes the whole thing very challenging, because you need to add extra lenses, but this extra lenses also perceive the light from the display. So it suddenly affects the overall system. And there are a couple of really cool systems, and I really like this one, even though it was one of the first one from Kiyoshi Kiyokawa's group. I think this is a paper from 2003, and what I really like that he identified the problem already back then and has a kind of cool solution. And why this approach or this head-mounted display prototype that he presented looks so complex is because he tried to also compensate of the shift, of the viewpoint shift introduced by all these different lenses. So he introduced new lenses and then introduced other lenses to compensate for the effect of the lenses first introduced. And this is what makes it so complicated. Of course, other people have also looked into that, and it's still an active research area, but I still wanted to show it, and you still see the effect from no occlusion on the lower left-hand side to relatively sharp occlusions on the lower right-hand side when you really see him and his sense occluding the world. Okay, so and I think it's a pretty cool approach. One other problem related to occlusion that I also have missed for years is the problem that they also need to be varifocal. Because the one thing is, yeah, we can introduce a new optical lens, and then we can move or can create actually a sharp focus mask. But the problem is now, if we have varifocal content, so for example, if the teapot can now be on different focus planes, then the occlusion mask from the teapot also needs to be on different focus planes. Okay, and there's also increasingly more work on that so here's an example again. So basically what you see there, I'm not even sure what this element is. It's like, looks like a screw. So basically with a focus mask, and the focus mask behaves like it should be behaved. So basically, if I focus on that screw, we have a sharp, the screw is in focus, but also the focus mask, so the occlusion mask, sorry, is in focus, and the background is blurred. But if I now focus on the background, then the screw, so the image is blurred, but also the focus mask. And this is how it should be, but only if I have a system with varifocal occlusions. Most of the systems for that, they actually only demonstrated in LED setup and relatively complex optics. But again, that needs to be solved also in a mobile prototype. I get at this point, we already reach a kind of information overflow. And given that I have the luxury that I also have the next session on Thursday, I would say we make a quick stop here. I'm on slide 71, and there are roughly 10 more slides to come. And I would wrap it up for now, and to also be able to answer a couple of questions if you have some. And then the remaining time we talk about resolution, but also wide field, and I give a quick summary on Thursday to just stay in my tradition of always extending the lectures. Yeah. So for now, I would thank you. I skipped the slides, and we continue here on Thursday, and I'm there for any questions that you have. Thank you.